Hello, I'd like to discuss and demonstrate the ideal gas law. Here we have the ideal gas law. PV is equal to NKT. In this equation, P represents pressure, V is volume, N the number of molecules, and K is Boltzmann's constant, and T is the Kelvin temperature. Now, if we hold some of these variables constant, let others vary. For example, if we hold the volume and the temperature constant, then we can see that the pressure is going to be directly proportional to the number of molecules. Or more explicitly here, pressure versus N when we have a constant volume and also a constant temperature. Now I'd like to demonstrate that with the aid of this pressure tank. Here I have a tank that's pressurized to a gauge pressure of 60 pounds per square inch, and the gauge pressure, of course, is related to the absolute pressure, which is in the equation there. So as I release air from this tank, we'll notice as the number of molecules decreases, the pressure will also decrease. Currently we have a pressure of 60 pounds per square inch on the gauge, and I'm going to release some air, and we're going to drop that pressure down. And let's see what happens. So I dropped that down to a pressure of about 40 pounds per square inch. So we've had a pressure change on the gauge here from 60 pounds per square inch to 40 pounds per square inch as we released the air from this cylinder. The gas we're working with here is air, and we see that the pressure decreases as the number of molecules decreases in this pressurized cylinder. Similarly, if we were to do something like add pressure to this by hooking up a hose to it or a pump and adding air, we would increase the pressure in much the same way we do when we pressurize our automobile tires. By adding air, increase the number of molecules, that increases the pressure in the tire. Next, I'd like to demonstrate the ideal gas law, where we keep the number of molecules and the temperature constant and let the pressure vary with the volume. Here we see from the equation that if the number of molecules is constant and the temperature is also constant, that the pressure and the volume vary in an inverse relationship. I'd like to demonstrate that with the aid of this apparatus. Here I have a piston and a cylinder with a gauge. I'm going to put this on the overhead projector so that you can see that a little better. Now that this is on the overhead projector, we notice here I have a piston and a cylinder in which I can change the volume in this region of the cylinder. Currently I have it unconnected. I'm going to connect this up to the pressure gauge, and then we're going to see what happens when I reduce the volume or increase the volume. And the gas we're working with here, of course, is air in this cylinder, and also the air in the line and over into the gauge. So we have a certain volume that we'll be changing, and I'm going to set this arbitrarily here at 32 cubic centimeters, and then connect this up. And then we see we have a pressure of 15 units, and I'm going to reduce the volume, and notice how the pressure increases. If I reduce the volume to about 17 cubic centimeters, the pressure now is up to about 26.5 units. Letting the volume increase, the pressure will again drop back down to atmospheric pressure, and then from there, if I increase the volume, then the pressure will actually drop below what it was initially. down now to about 13 units, and back to 15 units, which would be the same pressure in the cylinder as we have in the atmosphere, and we notice that that's the case. This demonstrates the relationship between volume and pressure for an ideal gas. Next, I'd like to demonstrate the ideal gas law when we hold the number of molecules and the volume constant, and we watch the pressure vary with the temperature. Here we see from the equation that if we hold n, the number of molecules, and v, the volume constant, that as we change the temperature, the pressure will be directly proportional. I'd like to demonstrate that here with the aid of our pressure gauge that we used in the earlier experiment. And this time use a bulb here that I will put first in some cold water, some ice water, and then in some warmer water near the boiling point temperature. So let's demonstrate that first by measuring the temperature of the water here, and we see that indeed it is 0 degrees on our Celsius scale, temperature of ice water. Technically speaking, and it's very important to note that the T in the equation there is the temperature in Kelvin units, but we're measuring here the temperature in Celsius units, and of course there's a relationship between Celsius and Kelvin. We're measuring the temperature of the ice water to be 0 degrees Celsius, and then I'm going to put this bulb in the ice water, totally immerse the bulb in the ice water. There's air in here, so the gas we're using is air, the atmosphere. And then I'm going to connect this line up to our gauge over here, which I will now do. So as I connect this up now, we have a complete loop here where the pressure that the gauge reads will be the same as the pressure that's in this bulb. Currently it's at about air temperature and atmospheric pressure, and as I put this in the ice water, let's see what happens to the pressure as the temperature drops. So we see the pressure drop from 15 units to 14 units. And that's not very much because on the absolute scale of Kelvin degrees, the percentage of temperature change is not that great. Nevertheless, we see that a change in the temperature, a reduction in the temperature, causes a reduction in the pressure. Next, what I'd like to do is put this in this water, which is up to a temperature of boiling down near the bottom, and let's see what the average temperature of the water is here on our Celsius scale. So I'll immerse this sensor in here, and we can see the temperature of the water is above 92, it looks like 93 degrees, something like that. And if we were to reach the equilibrium boiling temperature for water, we'd find it would be about 94 or 95 degrees at our altitude here. But significantly higher temperature than the ice water. And let's see what happens now to the pressure inside this bulb. Still very cool here. And let's see if we can get the pressure to increase in the bulb as the temperature of the bulb increases. Now you can see that the pressure has increased as the temperature has increased, indicating that there's a relationship between temperature and pressure for an ideal gas. When the volume is constant, when the number of molecules is constant, as we increase the temperature, we also increase the pressure. Next, I'd like to demonstrate what happens when we hold the number of molecules and the pressure constant and let the volume vary as the temperature varies. Here we see from the ideal gas law that if we hold N, the number of molecules, and P, the pressure constant, that as we increase the temperature, we also have to increase the volume. I'd like to demonstrate that with this little simulator here, in which I have in this chamber here some little glass BBs similar to those that I have in this jar here. So we have some glass BBs in here, and there's a disc in here which will then start those BBs into motion. As that disc spins, it's got some little bumps on it. It'll start those BBs into motion, and that will simulate an increase of temperature in our simulated gas in this chamber here. And we'll see that that will cause the volume to increase as the pressure is going to remain essentially constant. So with constant pressure, constant number of molecules, we're going to see the volume increase as we simulate a temperature increase. Now I'm going to turn this on and start the disc spinning. That'll start the BBs into motion, simulating a gas with molecular activity. I'm going to first set it at a particular average speed, and then I'm going to let the volume increase, and you'll see that happen. And then I'm going to turn the speed up, and again we'll see the volume further increase. So now we see that as we hold N and P constant, that the volume varies directly as the temperature. This completes our demonstration of the ideal gas law. Pressure times volume equals number of molecules times Boltzmann constant times Kelvin temperature.